Okay, good afternoon, everybody. My name is Ronnie, and I'm located just one floor below this one. The worst time to have a lecture is right after lunch, right? So here we are. But we have to somehow push through. And what helps is if we are discussing and we are engaged and we are not falling asleep, okay, during the course of the lectures. I want to start with an overview of what we are going to learn and discuss. And I want to split it this year in a lecture student Tirgul format. Simply for the reason that I don't have Mefagel that can present these in-depth topics and also helps with checking exercises. So I decided I won't check exercises every week for 50 students. And we instead do Tirgulim, and everybody who does not want to give a lecture will submit at the end of the semester a notebook with on a particular topic, particular project. Okay, so we would start today with an introduction and power laws. David, since I see you here. So there will be some overlap with complex systems. We will go here in some instances, for example, when we talk about calculation, we will go more into detail in this course, and other things that we discussed in the complex systems course we will not touch. So we will not do extensive analysis of data, for example, and we will not talk in detail about scaling laws and stuff like this, but we talk about power laws. Okay, and this is today's topic. Next week I give another lecture on fractals, the theory behind how we calculate fractal dimension, what it is, and then we have a lecture, last lecture before Pesach, will be on calculation, and after Pesach I'm doing this because the optimal way would be that we have 1 week I give a lecture about the theory, and the next week one of you guys is talking about an in-depth topic on the big overall subject, right? So if I talk today about power laws, would be good to have the next week somebody of you talking about what is maximum likelihood estimation, for example. But it would be impossible for you to prepare this in 1 week. This is why we start with the student lectures only after Pesach, okay? And I will post a list on Moodle where you can put your name and whatever topic you want. So there will be these student Tirgulim, the talks, the lectures by you guys, and there will be paper projects that you submit at the end of the semester. Okay? And yeah, so after Pesach we start covering basically today with some in-depth discussion on what is maximum likelihood estimation. It will be one student will talk about this, okay? And another one will talk about Zipf's law. What is it? Where do we find it? Why is it relevant to physics? Then the week after, we will cover the second lecture with fractals, and someone of you will show everybody else how to draw a fractal, okay? And in this particular case, the Koch curve, and someone else will talk about the logistic map, okay? So that's the logic. Then the last thing will be on calculation, and after this we have this alternating lecture Tirgul meetings, and yes, in this way I hope we will cover a lot of material, and we will be everybody will be happy. Good. Any questions on this? Here, what we are going to do. Good. So about the grading, I already talked about it. So I mean, first we have the 6 topics, 6 lectures, and 6 turbulim. 2 specific topics. So in each turbul we have 2 specific topics to be covered. And I will post this list on Moodle, on Levida. Grading will be based either on the presentation or on the notebook that you are going to submit, and the way you present in the lecture, and also how you submit your final work, your project, is by using a Jupyter notebook. Everybody's familiar with Jupyter notebooks? No? So I will talk a bit about this at the end of the lecture. Okay, I have some Jupyter notebook and I go over it with you guys together. The advantage of the Jupyter notebook is that you have the code, okay, your programs inside, and you can also type like in LaTeX. So it's very convenient to my opinion. Yes.
I have a question. Are we going to do both the presentation and the final project, or either one?
Either one, because all together you're 50 students, and we won't have the time for everyone to present, but not everybody also wants to present. There are many students that usually don't like to present, and they prefer to submit something at the end of the semester. Yes?
The presentation is individuals.
Presentation is what?
Individual.
If you can do it in couples?
Yeah.
Oh, yeah. You can also do it in couples, but I don't want to have you coming with your friend and you're giving all the talk and your friend is just standing there and says yes, yes, yes. So it has to be equally distributed, okay? So, yeah.
If I try to do the presentation and it doesn't go very well, can I do the final project as well?
Yeah, but usually it goes well. And it's also recommended that before you give your presentation, you come to visit me and we go over it. Okay, that you're covering what I imagine you to cover. So the best is you first come to talk to me what you should present, and then later perhaps you come or you send me your material and I will give you feedback. But usually it's fine. It's much easier to do a presentation than to write the project in the end. My opinion. Yes?
The presentation would be on the lecture time?
Yes, yes.
And how much time for each student?
So we have 1.5 hours, so I would suggest 40 minutes presentation. And it has to be, I mean, we have it's computational physics, so you need to learn also a little bit programming, right? So, the one that presents really should go over parts of the code. I mean, not the simple stuff, you know, but the things that are important to, for example, print the fractal. How do you do this? Okay, recursively.
What I'm asking is, do you need a PowerPoint presentation like, or just the Jupyter?
No, you just do Jupyter. Just do Jupyter, and Jupyter you can also include figures, you can plot figures, you can write text. It's very convenient. Good. Okay, so you have learned in the semester Aleph about numerics, right? So what's the difference between numerics and computational physics? Any idea? So what did you learn in numerics? How you solve, how you integrate numerically, right? How you generate random numbers, I guess, right? We also discussed probably Monte Carlo simulations,
Yes.
right? And you solve differential equations, perhaps, also, right? And so what is all this? Basically, these are all tools, right? So you learn tools how to solve mathematics, so to say, on the computer, more or less, right? So, and computational physics is also using numerics, but we want to solve physics problems, right? Obviously. So, when you plot, the domain of computational physics, then you would put it between theoretical physics and experimental physics, right? You have an overlap between the two, of course, but computational physics is kind of another field of physics that benefits both experimental physics and theoretical physics. In fact, in the most recent years, this is the field of physics that has grown the most. For obvious reasons, right? We have only in the last couple of decades we have powerful computers that can solve questions that we could not solve analytically. So some of the problems in physics we can only solve by numerics, right? And for this we need the numerical tools that you learned in semester Aleph. Simulations of complex systems is a big part of computational physics. And we will talk about this. And yeah, for this reason, one could say that computational physics is the third column of physics. And that's all about computational physics I want to talk about, because everything else is too much going into detail and it's too boring. Any questions about this? Okay, good. Most of it you already have known before, I guess. Good. So then let's go to the first topic, which is power laws. Okay? What are power laws? Stupid question and easy answer. It's just a special kind of a probability distribution that follows. If this is the probability, then the probability is proportional to a variable x to the power minus alpha. Okay, and then you have also a constant there. And for what is the constant good for? Why do we need the constant? We need to normalize, since it's a probability, we need to normalize it that it's equal to 1, right? When you do the integral over the whole distribution, you should end up with something that is equal to 1. So this is exactly shown here. Of course, in physics, we only look at positive values, right? You can also, in mathematics, you can go from minus infinity to plus infinity. Physics doesn't make much sense to go and look at negative measurements, right? So you do the integral, you obtain 1, and then you can determine your this constant, normalization constant, and it is just when you plug it in into the integral, you get 1 minus alpha divided by x min to the power 1 minus alpha. And now when you take this c and put it back into, it's very annoying here that they put this point in front of it. So I often have to switch to here that you can see what is hidden there. So you plug it back in and you get this as a probability distribution, right? Nobody can see this at the end, but you can turn around, right? Okay, good, perfect. Here are some examples how this probability distribution looks like on a log-log plot. Right? When you do log-log, you get a straight line. Where you have 3 examples and copied from a book. where it is also in black and white, which is very stupid because you don't see what is what, right? Everything is in black, but the author of this book assumed that everybody knows what is meant by this. So there is 1, 2, and 3 here. Someone can tell me?
Top to bottom.
From top to bottom. So if you have 3 means so x to the power minus 3, you have a steeper decay, right? And alpha equal to 1 is a more smooth decay. What is the problem with alpha equal to 1?
Just 0.
Hmm?
0.
What's 0?
You can't normalize it.
Good.
You can't.
Almost what?
You can't normalize it.
Exactly.
Like that.
It's complete. I mean, it's a problem, right? If you plug in alpha equal to 1, you see that you cannot normalize it. You cannot integrate, basically, right? So this is a special guy, alpha equal to 1, that we will discuss, or one of you will discuss, when we talk about the Zipf distribution, because the Zipf distribution has exactly an alpha equal to 1. Okay? Good. If there are any questions, you just shoot, okay? You don't need to be polite. I'm not polite with you either. So. Okay, so perhaps you're not so familiar with power laws, but you learned a lot about exponential distributions, right? We have exponential distributions everywhere. What is a big example of exponential distribution?
Gaussian distribution.
Hmm?
The Gaussian
Yeah,
distribution.
Gaussian, right? But in physics, I mean, Gaussian
Everything.
is everywhere, yeah, almost everywhere. But Gaussian is not a power law, right? So, but you already learned about nuclear decay, right? Nuclear decay? Yes or no? Yes. Okay, so nuclear decay is an exponential distribution, right? Good. And here I plotted, so power law we just learned is x to the power minus alpha. Exponential distribution, you know, it's e to the power minus lambda x. And when you plot them, again, log-log plot, straight lines are the power laws, right? Here are the numbers, so 1.5, and this is 3.5, minus 3.5. So exponential distributions are behaving like this, okay? So we have a much faster decay for an exponential distribution. So here you have lambda 0.1, okay? Then you have the more smooth decay, and if you have 2.5, it's decaying faster. Good. So if you would divide now the power law by the exponential distribution, so you want to see the difference, where's the fundamental difference between the two, then you end up with a plot like this, and you see that for small x, they're not so much different from each other, right? Not so much different, but they get very different for larger x, okay? As you can see here, the power law has a what is called fat tail, okay? So events that for an exponential distribution are very unlikely, they become quite likely for a power law distribution, okay? So something that is effectively impossible has a negligible probability under an exponential distribution becomes commonplace under a power law distribution. This is what you see here. The larger the x is, the more different is the power law from the exponential distribution. Why are power laws important? Because we find them a lot in nature, okay? And if you find something a lot, it means it is not completely steuert, okay? So if we see a lot of some things happening in nature, then it's supposed to tell us something. So if you look at different processes or different domains in nature, in sociology, in society, you can find power laws almost everywhere, okay? And so if you take a distribution of family names, you get a power law. Someone can explain me what we see here?
If you look at the
Yes.
number of people with a certain family name,
Yes.
slowly, see you're getting power laws.
Yes.
distribution.
So who are these guys? Which family name do they have?
Where?
Hmm?
Where family name?
Yeah, let's say in Israel.
What?
Let's say in Israel.
Example for our family?
Yeah?
Dilmoni.
Really, I would have said Cohen.
Ah, where?
Yeah. These are people with the, there are many people. I mean, okay.
Ah, okay.
This is from the United States, okay, because we have 1 million people in Israel. There are not 1 million Kohanim, but let's say, I mean, let's say this is 2 orders of magnitude below. Then this would be the Kohanim in Israel, okay. In Germany, it would be Müller or Meyer, okay. So a lot of people are having the same family name. This plot would not work in China. Why? Because in China you only have 3 kinds of family names, right?
Yeah.
Or 4 kinds. You are special. You have you would be here somewhere, but you have Ma, Li. What else?
Many. As the number is about 100 now. There are about maybe thousands of others. They share this.
Okay, so you have dozens. You have
Yes.
but there are not many options. I don't really know why, actually. But maybe we make this a project. Somebody researches why in China they have all the same name. Good. Wealth distribution. Power law distributed. Okay. Who is this guy? Or girl? Huh?
Elon Musk.
No, this is Elon Musk.
Why?
Because he has
okay.
most of the money.
Yeah.
Rabbit, we are here somewhere. So these are the poor people. And, I mean, not very poor, but these are the Elon Musks and Bezos, and I don't know who's the third one. Some French guy, right? Or Bill Gates lost a lot of money. He got divorced, so he had to give half. He's only below the top 10. Citations of papers, okay? Very influential papers, cited many times. A lot of papers cited only a few times. What else do we have? Flares, solar flares, power law distributed. You have a lot of small ones, but sometimes big solar flares.
What it is?
Solar flares? This is when you look at the sun, you have these kind of eruptions there, right? That have different size distributions. And this affects also Earth, right? Because if you have some eruptions there, we get more of the solar wind. Okay, I'm not expert on this. I just a few things I know about it. Earthquakes. Earthquakes. You have a lot of small earthquakes and a few big ones. These are followers of religions. Also power law distributed. Many sects with a few followers, and I wish this would be Judaism, but it's not. It's Islam. I know this is Christianity. This is Islam. Okay, and I think then you have the Buddhists, and we are only in number 4 or 5. Can it be? No, it cannot be because we are. Okay, so I don't know. I know that this is Christianity, this is Islam, and I don't know about and Buddhists, but where we are, I don't really know. Good. When we characterize power laws, or in statistical physics in general, then you want to learn something about distribution, you calculate the moments, right? What are moments? In common terms, what is the first moment?
X.
The first moment is the mean, right? We call it average or mean. And then we have the second moment, which is the variance. The third moment is some skewness of a distribution, and there are all kinds of moments. How do we calculate moments? We simply multiply x to the power k. Okay, x is our variable to the power k. K is which moment we are looking for. If it's the mean, then it's just k equal to 1 times p of x. And we plug it in and we get, we can easily integrate this, right? It's just, you have minus alpha, you integrate it, you get minus alpha plus 1, and you have also k, so it's plus k, and you get something like this. And what is the problem with this one? When you solve it now?
Infinity, it can be infinite.
Okay, so this needs to converge, right?
So k has to be lower than
So yes, so this has to converge, and it converges when the exponent is negative, right? It's negative, so alpha has to be above k plus 1. Okay? Very well. So it converges only when alpha is above k plus 1. So now we learned something about alpha already on the first slide. Amos? Amos?
Oh,
No, we? Oh. Os, yeah, sorry. Os. What did we learn about alpha?
must be bigger than 1.
Has to be above 1, right? Otherwise we cannot normalize it. So, so if alpha is bigger than 1, then we see that for having a distribution where alpha is between 1 and 2, switch here, we won't find any moment, okay? This will diverge, okay? We cannot solve the integral. It will diverge, so the moments do not exist. So it doesn't make any sense to have a distribution with a alpha between 1 and 2, and to ask about what is the mean of this distribution, what is the variance of this distribution, because they don't exist, right? They don't exist. If you are between 2 and 3, then you see that it works for the first moment, okay, but it does not work for the second moment. So you have a mean, but you don't have a variance. Okay, you cannot calculate the variance. So altogether, when you want to write it in general, here, so it would be basically xk, so we just take this from above, xk min, alpha minus 1 divided by alpha minus k minus 1, and this is true only when alpha is larger than k plus 1. Good. Now you can say, yeah, but I have, when I have numbers in, I collected some data points, and I can always calculate the mean and the variance, right? So what is the catch here? Of course you can do it, but what is the catch? Yes.
So ours would be just infinite. Not
Yes, so what we have to distinguish between the sample mean and the sample variance, or sample moments, and population mean and population variance. What is this here? When you calculate theoretically the moment of a distribution, what do you get? It's a population mean, population moment, population variance. And when you have data, you have a sample mean, a sample variance, okay? So and when you do this, when you generate data in your computer that are power law distributed, okay, of can take of sample size 10, 100, 1000, 10,000, and so on. And if you have a exponent of 1.7, we learned that there's no mean and there's no variance, right? Of course, you can calculate the sample mean, you can calculate the sample variance, but it will never converge towards a fixed value, right? A constant value. It will increase with the sample size. That's what you see here. It's not bounded by anything, okay? They just diverge. However, if you take now a distribution with an alpha of 2.05, okay, or slightly above, you're having now a mean, but you still don't have a variance. And exactly it's what you see here. The red one is the population mean, and the larger your sample, the closer you get to the theoretical mean that you calculated from your distribution, right, at the moment. And of course, when you have above 3, then you will also converge your population variance towards your population variance. So if the take-home message, if a moment does not exist, is infinite, the sample estimate grows with sample size n. Good. Now, an important property of power laws is that you can easily rescale them. They are scale invariant. So, given a PDF of p times c, so you have values of x, right? And now you multiply all your values by a constant number, right? C, some constant real number. So when you plug this in, very easily you see that you can just take this out and you get some scaling factor, c to the power minus alpha times pc. So what does it mean? It means that we can just rescale our PDF, our probability distribution, by this constant c to the power minus alpha. And what does it mean graphically? When you think about it, you have this power law distribution, you have this straight line. What does it mean now by multiplying it by c to the power minus alpha?
It will decay.
You just shift it. You just shift it parallel. Okay, you can shift it up with a positive c, or shift it down with negative c. So you just do a parallel shift of your distribution, so to say. So, but this in turn also means that if you find two power laws with the same exponent, they are basically the same. Okay, because you can transfer the one into the other just by dividing by c or multiplying by c to the power minus alpha. And this you can only do, this trick you can only do with power laws. Okay, very handy way of working with power laws. One tip of how to plot power laws. You have here 3 examples. Same power law plotted 3 different times. Which one would give you all the points in your for your submitted work, and which one would not get you points or less points? What do you think?
The middle one is very noisy.
Middle one is very noisy, yes. What about this guy? It's not obvious that this is really power law, right? It's we said we want to have it plotted on a log-log plot, right? And to have a straight line. So this one is really the winner. Why? Because, yeah, for the reason that here we cannot clearly identify it's a power law. Here, I mean, we are quite interested in what is the behavior at the long tail, but we cannot really identify it because it's so noisy, so much fluctuating. And here we have a more or less straight line, right? That is preferable. Why is this happening?
alpha is between 1 and 2.
What?
Because the alpha of the B is between 1 and 2.
No, the alpha is the same everywhere. Here's the same alpha, these are the same data, okay? Same data plotted differently. What's happening here? What's the difference between these two guys?
Sample.
Hmm?
Sample scale.
The samples what?
Sample scale.
No, it's not scaled. It's just the bins, okay? I mean, you have to do some binning, right? And the bins here are linear. So it means that you have always the same little bin. So in the beginning, so you have the same little bin that you try to fill with your data, right? And then you come, in the beginning this doesn't matter much because you have so many data that fit into the bin that there's no problem, no fluctuation. But when you come to very large bins, then you will, no, very large values, but the bin is very small, right? So sometimes you have a case, a scenario, where you only have a few data points that fit in this little bin, okay? And then in the next bin you have a lot that fit inside. So it makes a lot of, it causes a lot of fluctuations. Sometimes it's even empty, okay? Then you get 0. And how to avoid it? How do we get this one? By adapting the bin size, okay? When you are at small scales, when you are here, you take small scales, you take small bins, and when you go to larger values, you adapt the size of the bin logarithmically. So here I have a logarithmic size bin, so a much bigger bin that covers more data, okay? So it's not fluctuating so much.
So C is a log scale, and what is D? Also log scale?
Linear scale, log scale with linear binning, log scale with logarithmic binning. Okay, and if you have time later, I show you a small script how to do it in Python to get log bins. Good. Any questions so far? Good. So let's talk a little bit about the origins of power laws. From where do we get power laws? And there are many different processes that generate power laws, but the most common are the 6 that we have here. Yes, even 7. 7, yeah. 7. One is what we know from statistical physics and thermodynamics is phase transitions, or when we are at criticality, right? You learned about the Ising model, I guess. Good. This is an instance where we get the power law. We'll talk about it in a minute. Self-organized criticality is another process. Then we have a process where we just multiply numbers, okay? Multiplicative processes generate power laws. We have processes that have a preferential attachment, or it's what's called the rich gets richer phenomenon, explaining this power law for the rich guys. You remember it was where Elon Musk was on the bottom. Now Tesla is losing a lot, so probably maybe Bezos will take over. I don't know. So these are these preferential processes. We have sample space reduction processes. We'll talk about it in a bit. And we will have one lecture about fractals, why fractals generate power laws and why we find power laws in calculation. But this will be in more depth in the next week and the week after. And these 4, 5 we will just briefly discuss now. Phase transitions. So when you're at the critical point, we have learned in thermodynamics and statistical physics that physical quantities, they start to become global. Okay, so it's not just that if you go to the Ising model or spins in general, magnetic spins, that they only feel their next their neighbors, right? Which is the case when you are, let's say you look at a transition from a paramagnet to a ferromagnet, right? And when you have a ferromagnet, the spins only feel their surroundings, so to say, right? So now you cool down your paramagnet, and in some, not always, but let's say it's a ferromagnet above DC, you cool it down, and what's happening is that the spins start to feel a bigger environment up to TC, where basically they theoretically feel globally what's going on, right? I mean, so it's like their feeling and their, I mean, it's very hand waving, but they feel the whole surrounding, so to say. I mean, we know it's mostly in domains, right? But this is on a macroscopic scale. So global correlations emerge, and the spins start to feel the entire system of magnetization, and we can characterize this, right? You have learned about the susceptibility that you can write like this. So it's T minus TC divided by TC. So basically, how susceptible the spins are at TC diverges, right? So it becomes infinite. And it diverges by this exponent minus gamma. So it's a power law, and we have this exponent minus gamma. And when we are at these transitions at criticality, we call them critical exponents, right? And they are very important in physics because if you have materials that share the same critical exponents, you can put them into a universality class. Okay, so it tells you something about the physics that's going on in these materials, only because they have the same critical exponents. And so meaning if you have different materials where the critical exponents are the same, then the physics is the same, right? And even better, if you come up with a model, and in this model you get certain critical exponents that you find also in your experiments, then you can say, my model explains exactly the physics that's going on in this material. It's phenomenal. This is really great. And the reason why this was a Nobel Prize also for the discovery of this universality classes. Good. Self-organized criticality, another process that leads to power laws. And what is a self-organized criticality process, or a system that shows self-organized criticality, is something that is a system out of equilibrium, first of all, and it has a critical point as an attractor. When you have a normal phase transition, water to ice, paramagnet to ferromagnet, this is not a, it's not, so the critical point here is not an attractor, right? So you have to fine-tune your experiment to be exactly at the critical point. When you want to freeze water to ice, have you done this in an experiment? To keep it exactly at the critical point, that it doesn't become ice, and it's, I mean, that it's exactly in between. It's very difficult to achieve this. It's not very, but it's you have to do some effort, okay, to keep it exactly at the critical point. For a SOC system, for self-organized criticality system, you don't need to do this effort. The system is kind of pushing itself always to this critical point. Okay, it's like masochist. Okay, it's all the time putting itself in the critical state. If it's away from it, it puts itself back. So they don't need to be fine-tuned from the outside, but they find themselves the critical point all the time. And this one way to understand the scaling laws. And a famous example, I mean, actually the first example from the guy that coined the name self-organized criticality, which was Per Bach. He came up with this sandpile model. Okay, so you're going to the beach. It's Rat Hashem soon. Now it's getting warm. You can go back to the beach, and you can build with your children or nieces or nephews or whoever, or by yourself, a sand pile, right? How do you build a sand pile? You just randomly put grains on top of each other until you get some little mountain. And what happens from time to time? Collapses, right? It collapses. First of all, it's something that is slowly driven. It's non-equilibrium, and then you have these collapses, these avalanches, and you have avalanches of any size. Sometimes only small ones, or many times small ones, and from time to time big avalanches. Okay, that almost destroy your complete nice sun castle, and then you build it up again. And so when you look at the size of these avalanches, you get the power law. Okay, and when you look at the waiting times between the avalanches, they are exponentially distributed. So it's more or less random, right, when they collapse. And so this was proposed by Per Bach and Tang and called Wiesenfeld, and it sounded all very nice. Until someone, a famous professor by the name of Jens Feder from Norway, he said, okay, this Per Bach guy, he only suggested this theoretically. He has never measured it really by going to the beach. Let's measure it in the lab, okay? And what he found is that actually this is not a self-organized criticality process, but you get self-organized criticality when you do what, David? You take ores. It works with ores, but not any kind of ores. You have to have basmati rice, okay? Why you need basmati rice? Because of the shape. Two things. It's not so sticky like normal rice, and it has this shape, and you need this shape, this football-like shape, for energy dissipation. Okay. Otherwise, you don't get a nice power. So much about theory and theoretical physicist, right? This guy is theoretical physicist, and he is both. He is theoretical and experimental physicist, and yeah. So this is one. This is the lab, and then so this is the model that Bach, Tang, and Wiesenfeld suggested. It's very simple. That's why I wanted to also tell you about it. You basically, when you go into a 1D kind of this model, you can imagine you have some kind of stairway, okay? And now you drop on the top of the stairway, you drop your grains of sand, so to say, until you reach a certain threshold. So each stair can only carry a certain amount of sand, right? When you are above this threshold, then it will collapse onto the next stair, right? And if it crosses the threshold there, it will collapse to the next one, right? And you can imagine that you will have many of these small avalanches, but if you have everywhere filled up, your sand is filled up to almost the threshold, then even a little grain, okay, they all the time say this is the last drop that exploded the barrel, right? So here in in comparison, it would be a piece of sand grain that would trigger everywhere crossing the threshold, and then you have an avalanche. Yes.
It's like each rice grain is a stable equilibrium point.
No, each grain is putting your so here.
I mean by itself.
Yeah, by itself, it just increases in this simple model. It just increases your height. Okay, and when it goes above some threshold, then it all collapses and transfers to the next step. So that's a simple idea. You can do this. This is 1D. You can do this also 2D, right? And 3D. Then you have some cube, and you fill inside the cube some sand, and you look how it changes how the avalanches emerge. So another example of self-organized criticality is earthquakes. Okay, we saw before that earthquakes show this power law. Okay, we have many earthquakes with a small magnitude, and we have a few earthquakes with a large magnitude. Here's distribution of earthquakes over the world in '95, and plotting this is called Gutenberg-Richter law. You probably have heard it. It's all the time said in the news. There was an earthquake, and with magnitude 6, 7 on the Richter scala, right? Or Gutenberg-Richter scala. So this is meant by this. So, and discovering this power law let people think about the mechanism. What could be the mechanism of this that the power law is generated, and as you know, how does an earthquake develop? You have plates moving against each other, right? And then you have force building up, and they are not smooth, so they are driven against each other, and they build up some tension, and this tension is released and leads to these eruptions. So this is example in geophysics. Then you can also go to physiology, sleep medicine, and find self-organized criticality there. If you look at the sleep cycle, usually what you see in the textbooks is that you go to sleep, you have light sleep, and then you go into different states of deep sleep, then you go into REM sleep, and you repeat the cycle over and over again. And but this is in the textbook. When you look at real data, you have a lot of these short awakenings throughout the night. Everybody of us has 10, 15, 20 of these awakenings. And when you get older, you have more and longer awakenings. Some of them you remember in the morning, some of them you don't remember in the morning. But of course, they're also short. Sometimes they are only visible in the EEG and your brain waves. You don't really wake up, but your brain looks like it's awake, but you are asleep. And you can plot this on plot the probability of these awakenings. Okay, so this is the probability of the awakenings over the duration, right? So you have many. This is now averaged over 30, 40 subjects. So you have many short awakenings with duration of less than a minute, and you have a few awakenings that are on the order of 15 minutes. I mean, if you have some elderly people, they have longer awakenings, and what you find is a power law. Okay, so they are power law distributed, short, and this tells you something about how the brain works during sleep. Okay, if you look at the durations between awakenings, which is sleep, right? The times between the awakenings and sleep, then you get an exponential distribution, right? So what is the typical time that we are asleep without any interruption? No, you can see it here.
20 minutes.
It's between 10 and 12 minutes. Okay, so these are healthy young people. So it's surprising how often you wake up throughout the night. Okay, so if you are in REM sleep, you have 10 minutes of REM sleep. So this is the characteristic time. Okay, so the characteristic time of your exponential distribution is 10 minutes. So you are 10 minutes in REM sleep, and then you have a short awakening. And then you either continue in REM sleep or you go into light sleep, okay? Depending on what your brain thinks is good for it. It's amazing how the brain self-regulates how much you sleep. One day, I don't know if you have this Apple Watch or Galaxy Watch that measures sleep. Someone of you has it? No? Yeah? So, I mean, they are not very accurate. But they have some things are okay. And have you noticed that one day you have more deep sleep and less REM sleep, and then the next night you have less deep sleep and more REM sleep, right? So it's your body adjusts depending on what was your daily activity in the day. If you did a lot of sports, you have more deep sleep. If you did not much sports, but you had to learn for Mifran, then you have more REM and light sleep, right? So it's amazing how it adjusts. But typically you're only at 10, 12 minutes sleeping without any interruption. Good. Referential processes. We talked about it. It's this rich gets richer phenomenon that in the Christianity they call it also the Matthew effect, and it's coined like this, that for everyone who has, he will be given more and he will have an abundance, and whoever who is poor will stay poor. Okay, this is basically their religion. So not very optimistic, but the important thing here is the probability of a particular outcome to occur is proportionally to the number of the outcome, to the number of times it happened before, right? So we will talk about this a lot when in the lecture on networks, because there's a model, Baruch-Albert model, very famous network model that exactly works based on this preferential detachment processes. Sample space reducing processes. These are basically processes that where future outcomes depend on the history of past outcomes. What is the most famous sample space reducing process that we know? If you just read the first sentence, what comes to mind? I forgot your name. Michal? Michal. Okay. Michal. You're smiling. What comes to mind? Life. Life is a sample space reducing process, because you make a decision today that will affect your future, right? If you are a baby or a young boy or girl, the sky is the limit. You can become everything. Okay, you can become a composer, politician, physicist, actor, soccer player, anything else. But if you're 65 years old, I'm not quite there, but almost, and then you cannot become any more professional soccer player. Not even in Maccabi Tel Aviv. Not talking about Real Madrid, okay? So, because you decided to study physics, then you were sitting the whole day and you became old and you became smart, but also a little bit more overweight. So there's no chance they take you. Not even in, what is the worst club in Israel? Polen. Oh, sorry. So, no chance, okay? Sample space is reduced, you cannot do this anymore. Good, this is life. Yeah? And so, simple models for driven out of equilibrium processes where the driving force brings the system to an excited state, which it then tries to relax towards equilibrium. Okay, not even I understand what is written there. But examples, what is we are surrounded by these sample space reducing processes. One is diffusion on directed networks. This is supposedly how Google search works, right? Because it goes into one direction and reduces the sample space to give you the right answer to your question. Evolution of language, fragmentation processes, and here somebody knows how to bake spaghetti? I mean in two parts. Have you done this? You cannot say this in Italy, that will kill you when you say you're baking spaghetti. But so let's say macaroni. Okay, how do you bake macaroni? You want to half them. Yeah, but what happens when you do like this just?
Will break, but one piece.
Yeah, you will not have two. You will not have two parts. You will have 3 parts. So
One is small.
yeah, one is small, but you want to have exactly 2.
You cannot.
You can. Here's a study by MIT. They put some money and brain into a study how to break spaghetti into 2 parts. Okay, and you do it the following: you turn it a little bit. What do you do by this? You reduce the sample space. You twist it a little bit, and then you break, and you get 2 halves. Okay? MIT, guys. Here's the link to the paper. This is one of the research that Donald Trump will abolish. Okay? It's useless research, but it's very interesting. And we had here a toy model for the sample space reducing process that generates the zip law, okay, with an alpha of -1. We said -1 is this borderline value that is actually problematic because we cannot really normalize our distribution. How do we get Zipf's law with this toy model? We take a die, a cubiot, right? You know this cubiot from Dungeons and Dragons? There are many, they are not just 6, they have many sides, right? So you take here one that has 13, and then you throw it, and you get 9, for example. So you take everything out that is above 9, so you reduce basically you change your cubiot. You do a sample space reducing process, so to say, and then you throw it again, you have 7, and so on. And if you do this many, many times, you generate a power law. Okay? So this is like a model of life. Okay? So every time you throw your cubiot, you will take out some of the options you would have had. Good. Any questions on this? Then I want to show you a little bit about around in these Jupyter notebooks. Okay. So I will put on Moodle a lecture from 2 or 3 years ago, given by my then PhD student that explains basics on Python and on Colab. Okay, so this is Google Colab. It's everybody who has a Google account can go to this website and can use by using this Jupyter notebooks can do programming. You don't need to install on your computer Python, you can just run it on the website, right, of Google. And this has the advantage that you can even do programming on your phone, okay, or on a tablet without installing anything. Just everything is here on the website. So I will put you some video on this on Moodle, and then you can start playing with this Jupyter notebook. So here, it's so bad because if I'm standing here, I'm covering everything. Okay, so I have to go back and forth. So, so the nice thing on Jupyter notebooks is that you write your text here, right? Just in LaTeX. So you see, this is just LaTeX, okay? Here you see how it looks like, okay? And then you can integrate cells with code, okay? And here is just because we discussed this today. Here is a little bit code about power laws. All the simple calculation that you had to do in your head when I showed you the first slide, how to integrate the power law and to obtain the normalization constant, you can also do with Python using this symbolic toolbox. Can you see it here? So the code for this is here. So you use the symbolic Python, and then you can do also an integral. Okay, you do an integral. You get here the. So you run the cell. I need to connect. Good, so you would run this cell. So when you see this, when it's like this, it's thinking, okay? Usually it's very quick, but in the first time you run the cell, it needs to connect to Google, to the Google servers, and then it just plots the result. Okay, good. So it plots the result, how it looks like. Then you do an integral, as we discussed. Here, you can just do integral. 0, 0 means that the integral goes to infinity. And when you run this, then you get what we already discussed here in the class. You get only a solution when it is larger than 1, otherwise you cannot integrate it. And then you can also calculate the C. So the code is all here. It's a little bit boring when I tell you everything. You can look at it at home if it's interesting for you. And what is more important, and also for the moments, okay, you can, if you have something, I mean, it was until 4 or 5 years ago, this was interesting to do, right? If you did have Mathematica and you wanted to do quickly an integral, you used the symbolic toolbox. Nowadays, you have ChatGPT, so you won't use it so much. Okay? I just wanted to show you, it's basically the history lesson. Okay? So 5 years ago, this was nice to have. Nowadays, not so much. However, what is important is what follows here, and it is about how to visualize the power laws, right? How to plot it. So you just have the examples, you can go over it when it becomes relevant for you. Typically what you use in Python is this matplotlib that creates figures that are very much aligned to a MATLAB style, okay? And you basically I mean, the syntax is very easy, and later you can just, when you have to plot anything, you can just copy paste from here. Okay. So this would be just plotting a straight line in on a log-log plot. So a power law that is generated by this formula here. And now you take for alpha different values, 1.5 and 2.5, and then you get surprise, straight lines on a log-log plot. But more important and more relevant is actually when you have random numbers that are distributed according to a power law. And a nice example is to take the Pareto distribution, that is a power law defined by b divided by x to the power b plus 1. So if you choose b equal to 0.5, it will be an alpha of 1.5, right? So you just generate 100,000 of these random numbers. You have 10,000, and you actually the above. So here's the. It's very easy. It's one line. Pareto size 10,000 generates you an array of Pareto distributed random numbers, and now you can plot them. Okay, you plot them, and it looks like this. On the log-log plot, that would give you 0 points in your submission, right? Why? Because it's also it's a log-log plot. It's linear. These are linear bins, and we don't want these linear bins, right? So how do we get now logarithmic bins? We just generate an array of logarithmic bins. You do this just by using here log space. This is 10 to the power 10, which is 1, until 1000, 10 to the power 3. And you want to have 10 of these bins, and then your bins look like this. Okay, these are log bins, 10 to the power until 10 to the power 3. And now you can plot the histogram. So I took here until 10,000 and 100 bins, and then you just plot the histogram, and you have now log binning. And if you look at the graph, it looks nice. Okay, not so much fluctuating like before. Good. So this is helpful, I hope, for you guys. Now, how would you? So you have now your distribution, and you want to fit the power law, right? How do you do this? You have one option to use polyfit, one routine that is called polyfit. Very easy. Here it's just one line, and you fit your histogram, and you get here your alpha, minus 1.5, which we put inside, right? We said b is equal to 0.5, so I have a power law distribution with an exponent of 1.5 or minus 1.5. So this I get here with the fitting, and you can just copy paste this for your projects. However, preferable is another way of determining the exponents, which is independent of choosing bins. Okay, so here you see the problem is always to choose the right bins, right? And you can do a lot of manipulations. You can choose, make the bins bigger or smaller, and then you can slightly change the slope of your fit, right? By doing this, by manipulating the bins. So a much better way of determining the exponent of power law is maximum likelihood estimation, which will be the first topic of the student tutorial in after passing. Okay, so if somebody is interested in talking about this, then he or she is welcome to give, make a presentation on maximum likelihood estimation. Good. Any questions? I will put the list of projects on Moodle with Ratoshem by the end of the week, and then you can, it will be, I mean, you can put your name inside, okay? But don't delete someone. So, yeah, respect if somebody is already put his name. Should I put it by the end of the week or by the beginning of next week? Because people who keep Shabbat would be in a disadvantage not to fill their name, and they will. I imagine they have done Haftalah and then they see the list is already full, so it would be not fair. So I will put it on Sunday, okay? On Sunday you will have the list and then you can put the name. Okay, any questions? So thank you very much and see you next week for the factor 4.